Last session, we talked about goals and importance of statistics. We said that we have two major types of statistics in language education. One of them is descriptive statistics, and the other one is inferential statistics. In descriptive statistics, we have three measures of frequency, measures of central tendency, and also measures of variability. In measures of frequency, we have simple, relative, and cumulative frequency. In measures of central tendency, we have mean, median, and mode. And for the measures of variability, we introduced variance, standard deviation, and range. We also talked about normal distribution and the usage of normality in second language research. Another topic was inferential statistics and the definition of inferential statistics in second language research. Finally, we talked about parametric and non-parametric statistics. Before, we said that statistics can be divided into two principal areas, descriptive and inferential statistics. Descriptive statistics are used to summarize sets of numerical data. Thus, descriptive statistics offer a tidy way of presenting the data we have. The important thing, however, is to note that these statistics do not allow drawing any general conclusions that would be beyond the sample. In practice, this means that when we report descriptive results, we ought to start every sentence which describes descriptive features with in my sample. If we want to say something about possible general lessons that may be drawn from our study, which is what we usually do when we conduct research, we need to compute inferential statistics. Therefore, broadly speaking, inferential statistics are the same as descriptive statistics, except that the computer also tests whether the results that we observed in our sample, for example, difference or correlation, are powerful enough to generalize to the whole population. It makes intuitive sense that what we find needs to pass a certain threshold of magnitude to be of general significance. Inferential statistics basically evaluates the results against such a threshold. If you remember, last session we talked about significance level and the threshold that in social sciences the p-value equals 0.05. So descriptive statistics are useful, for example, to describe the achievement of a particular class of learners. What happens, however, if we notice that, the L2 learning achievement of boys and girls shows a remarkable difference in our sample, with girls performing better than boys? So here, can we draw the inference that girls are better language learners? Of course not. Based on descriptive statistics, all we can say is that in this class, girls did better than boys. Pay attention. We can only say that in this class, and only according to our sample, girls did better than boys. In order to venture any generalization concerning the wider population and not just the particular sample, we need to show that the difference between girls and boys is significant in the statistical sense. So we need to employ inferential statistical procedures. The main concern of inferential statistics has traditionally been the testing of statistical significance. It denotes whether a particular result observed in a sample is true for the whole population and is therefore generalizable. One important feature of statistical significance is that it is the function of not only the magnitude of the result, but also the size of the sample investigated. The computer takes the combined effect of magnitude and sample size into account when it calculates the significance of a result. If a particular result is marked as significant, we can utter a sigh of relief, as this means that the observed phenomenon represents a significant departure from what might be expected by chance alone. That is, it can be assumed to be real and we can report it. However, if a particular result is not significant, we must not report it. For example, if the mean scores of the two groups are not statistically different, are not significantly different, we must not say that one is larger than the other one. Even if the descriptive statistics do show some difference, we should not report it because this difference was not significant. Significance is measured by a probability coefficient, shown by p, which can range from 0 to +1. For example, p figure of say 0.25 means that the obtained result might be due to pure chance in 25% of the cases. In fact, in social sciences, we typically consider a result significant if p-value is smaller than 0.05. That is, if the probability of the result not being real but only due to chance is less than 5%. That is 5 times out of 100. In that case, we can say that the result is significant. The selection of statistical tests depends on understanding the distinction between tests of relationships and tests of group differences. Generally, you will need a test of relationship if all of your variables are continuous. Look at this example. Is there a relationship between students' L2 reading scores and their scores on aptitude tests? So, as you can see, tests of relationships will look at questions of how strongly one variable relates to another, or which variables can predict scores on another variable. In fact, tests of relationships include correlation coefficient, partial correlation, and regression. If you have a mix of continuous and categorical variables, you will probably need a test of group difference. Now, see this example. Does input enhancement through reading affect EFL learners' vocabulary knowledge? As you can see here, tests of group differences look at whether membership in a particular category or group influences the outcome of, for example, some kind of test. Here it is vocabulary knowledge. Here we want to see if input enhancement in reading can have any effect on learners' vocabulary knowledge. So here we have a mix of continuous variable, which is vocabulary knowledge, and a categorical variable, which is input enhancement. Tests of group differences include t-test, analysis of variance, or ANOVA, MANOVA, ANCOVA, chi-square test. These are tests of group differences. Tests of relationships can be categorized as correlation, partial correlation, and regression analysis. In correlation research, no variables are manipulated. Correlational research, in fact, attempts to determine the relationship between or among variables. It does not determine causation. Correlations are calculated between, for example, two sets of scores. For example, one score can be the amount of talk, and the other score can be height. Then we can see if there is any relationship between these two scores, that is, amount of talk and the height. This is a very simple example for tests of relationship. Now we are going to talk about each of these three tests of relationship individually. The meaning of correlation in a statistical sense is very much related to the meaning you would think of in ordinary life. Correlation looks at how two measurements vary together. This can be either negative or positive. For example, positive correlation can be between listening ability and speaking. For example, you can say that the higher the listening ability, the higher the speaking ability. On the other hand, negative correlation would be between proficiency and number of errors one makes in writing. That is, you can say that the higher the general proficiency, the lower the number of errors that, for example, a student X makes in his or her writing. This is a negative correlation. And there are more formal methods based on calculations that give a numerical value of the degree of correlation or go-togetherness between two variables. The product moment coefficient of correlation, also known as Pearson's correlation coefficient, is calculated on the basis of how far the points lie from the best fit regression line. This is a correlation test that we use using SPSS in order to calculate correlation coefficient between variables. Correlation has a set of assumptions. One of them is this: the data are related linearly. The assumption must be tested by examining the data visually. That is, we use the scatter diagram to check this assumption. The next one is that the data should be independently gathered, normally distributed. And the third one is that the data are homoscedastic, that is, being capable of being scattered or having equal standard deviations. These three assumptions should be met in order to be able to run Pearson's correlation coefficient. Correlation has the following attributes. There are exactly two variables, and these variables do not have any levels within them. The other attribute is that both variables are continuous. We cannot have, in this type of correlation, of course, we cannot have one continuous variable and another, for example, categorical variable. Both of them are continuous. And the third attribute is that the variables cannot necessarily be defined as independent and dependent variables, although they might be. For example, look at this research question. Does amount of input that children receive matter to how much vocabulary they will learn in Spanish? This research question examines the relationship between the amount of input and vocabulary knowledge in Spanish. That is, the result can be something like this. There is a positive relationship between the amount of input that children receive and the degree or the number of vocabulary that they will learn in Spanish. For example, we can say that the higher the amount of input, the higher the amount of vocabulary that they learn. This is a positive relationship. Another study may examine whether intelligence and scores on implicit or explicit tests are related. That is, we have an intelligence test and we have scores on implicit and explicit tests. Then we run Pearson correlation coefficient. Note that the non-parametric alternative for Pearson's correlation test is Spearman's rank order correlation test. Whenever the data is not normal, for example, we can use the non-parametric equivalent of Pearson correlation, which is Spearman's rank order correlation test. The Pearson product moment correlation coefficient is symbolized by lower level case r. The product moment correlation formula has been conducted in such a way as to ensure that the value of r will fall within the range of -1 to +1. An r of -1 means a perfect negative correlation, and an r of +1 means a perfect positive correlation, and an r of 0 means zero correlation, which means that there is no relationship between the variables. So a high coefficient means a strong relationship. That is, if an individual scores high on one variable, he or she is also likely to score high on the other variable. In the example we just raised in the previous slide, for example, the higher the students, the higher the level of input, the higher the level of vocabulary knowledge. This is a high positive correlation. On the other hand, a coefficient of 0 suggests no relationship between the two variables. For example, there is no relationship between students' height and their English proficiency. Here we have no relationship. And negative correlation coefficients suggest inverse relationship. For example, the number of days students miss school is likely to have a negative correlation with their overall school achievement. That is, the higher the number of days students miss school, the lower their, for example, GPA, their grade point average. Partial correlation is the second type of correlation. Partial correlation is a technique used to determine what correlation remains between two variables when the effect of third variable is eliminated. Partial correlation controls for this third variable. In fact, partial correlation looks at the way two measures vary together when a third variable has been factored out of their relationship. For example, suppose that you are interested in the relationship between amount of L2 vocabulary knowledge and scores on a reading test, but you decide that it is required to factor the effect of age out of the relationship to get an exact picture of it, because you may think that age might have an effect on the students' vocabulary knowledge and their scores on the reading test. So here, age is regarded as a covariate whose effect should be partialed out as much as possible. In fact, as you can see, partial correlation is a very useful technique, allowing us to examine the relationship between two variables after removing the correlation, which is due to their mutual association with a third variable. For example, a background variable such as the learner's age, such as learner's intelligence, such as learner's aptitude. These variables can easily modify the scores when computing correlations between, for example, motivation and achievement. When you want to calculate correlation between motivation and achievement, you may need to partial out intelligence, students' intelligence. This is, in a way, the correlational counterpart of ANCOVA, which we'll talk about in future. Partial correlation has the following attributes. First is that there are 3 or more variables. You may factor out the influence of more than one variable at a time, of course. These variables do not have any levels within them, just like the previous correlation. All variables are continuous, and the variables cannot necessarily be defined as independent and dependent. Look at this question. How does age at which a learner began studying English as EFL relate to scores on a grammatical judgment test and a phoneme contrast test? So here it examines whether there is a relationship between age and test scores when the amount of total input is factored out. In other words, input is partialed out. Here we want to see the relationship between two variables, age and test score, when we control input. This is when we can use partial correlation, and this is why we call it partial correlation. Here we want to see the correlation coefficient of two variables, but it is partial correlation because we partialed out 1/3 variable, or maybe we want to partial out 2 variables or 3 variables. But the fact is that we want to see the relationship between two variables when we in fact partial out another variable. This is why we call it partial correlation. Third type of correlation is regression analysis. There are 2 types of regression analysis: single and multiple regression analysis. Regression is a technique that allows you to look at a number of explanatory variables and decide which ones have independent power to explain what's going on with the variable you have measured. It looks at the relationship among multiple variables to try to make a prediction about how some variables may predict scores on another variable and how much of the dependent variable can be explained by variation in the scores on the independent variable. In fact, in regression analysis, we want to have a kind of prediction. For example, we want to predict how ESL learners will do in college based on two factors: their results on a standardized test, for example, on TOEFL or on IELTS, and their performance in an intensive English program, IEP, on their own campus. Here we can use multiple regression. Multiple regression can help us to see if, for example, here we know a student's IELTS score. Can we predict that his or her IEP score can be, for example, X? This is the usage of multiple regression. For example, we might want to predict something right now based on a data that we have already. This is here we can use regression analysis. In fact, this type of correlation can be used when we want to see the composite effects of a range of learner characteristics, for example, aptitude, motivation, creativity, anxiety, etc., on achievement. Regression has a number of attributes. Number one, it has two or more variables. These variables do not have any levels within them. 3. All variables are continuous. And 4. Unlike correlation, one variable must be dependent and the others are independent. This is a major difference between regression analysis and the other two types of correlation. Before we said that we don't have dependent and independent variable, but here we say that one variable must be dependent and the others are independent. Look at this example. Can syntactic knowledge and vocabulary breadth predict EFL learners' reading comprehension test performance? Here we have a number of variables. Syntactic knowledge is one variable and vocabulary breadth is another variable, and EFL learners' reading comprehension performance is another variable. The researcher intends to investigate the relative significance of syntactic knowledge and vocabulary breadth in the prediction of reading comprehension test performance. That is, here we want to see if a student has certain, let's say, level for the syntactic knowledge and vocabulary breadth. Can we predict anything about his reading comprehension ability? Can we say that, for example, if a student has X amount of syntactic knowledge and X amount of vocabulary breadth, he may have Y amount of reading performance? Can we predict that? We have another statistical test that measures the relationship. In fact, the most commonly used non-parametric test in applied linguistics is chi-square test. Chi-square test investigates whether there is a relationship between two categorical variables. It is, as I said, a non-parametric statistic used with frequency data to test the relationship between variables. The question is whether there is a relationship between the number of people in each category, whether there is a relationship between the frequency or the number of people in each group or in each category. For example, we want to see if males and females differ in their choice of foreign language to study in high school, where the school offers Japanese, Spanish, and French. So here we want to see if there is any difference between boys and girls in their choice of foreign language. For example, boys prefer to study English or here French more than girls. Or for example, girls prefer to study Spanish and Japanese, something like that. So the question is this. Here, the chi-square test will calculate the difference between frequencies you observed and the frequencies you would expect in a particular situation and divide by the expected scores. Here, chi-square tells us the frequency of boys or girls who, for example, choose Spanish, or the frequency of boys and girls who choose French, and investigates if there is any relationship between these two frequencies, between the number of people in each category. Here we have two categories, males and females. Let us take a learner group of 40 students who have participated in a ballot by voting yes or no. The frequency of the votes broken down by sex can be put into a 2x2 grid like the one that you can see here. We have a table in which boys voted yes, 4 boys voted yes, 16 boys voted no, 11 girls voted yes, and 9 girls voted no. Looking at the figures, we cannot help wondering whether the students' gender influenced their choice, because there seem to be very few yes votes given by boys. If you pay attention, only 4 boys voted yes. But can you answer this question? Whether students' gender influenced their choice? Can you answer this question? The chi-square procedure can tell us whether there was a significant relationship between voting orientation and gender. This is the first part. The chi-square will tell us if there is any relationship between voting orientation and gender, and if there was any, we can find out how the figures in each cell are different from the expected figure. This is what chi-square tells us. Here we discuss two main uses of the chi-square test. The chi-square for goodness of fit and the test for group independence. Goodness of fit is used when we have only one categorical variable with 2 or more levels of choices. For example, we have one categorical variable like gender with 2 or more levels of choices. It is also referred to as one sample chi-square test, which explores the proportion of cases that fall into the various categories of a single variable and compares these with hypothesized values. The proportion of cases that fall into various categories, that is the proportion of number of, for example, people that fall into various categories, for example, into male category or female category of a single variable. This single variable is gender. Gender is one single variable with categories, various categories like male and female, and then compares these with hypothesized value. When if we have something in our mind, or previous research, for example, has showed something, we can compare our own proportions with the hypothesized values. The other use of chi-square test is the test for group independence. It is used when there are two or more variables and all of the variables are categorical. See the difference? In goodness of fit, we only have one categorical variable, but here we have more than one categorical variable. For example, one variable can be gender and the other variable can be, for example, being a smoker or a non-smoker. So smoking can be one categorical variable and the other categorical variable can be gender. Here, a test for group independence compares the frequency of cases, the frequency of people found in the various categories of one variable across the different categories of another. For example, here we can find the frequency of smokers and non-smokers in accordance with being male or female. That is, we can see if there is any relationship between gender and smoking. All in all, today, first we had an introduction to inferential statistics. Then we talked about statistical significance. We said that the threshold level, or p-value, in social sciences is 0.05. Then we talked about correlation. We said that we have three types of correlation. One of them is the simple correlation, which can be correlation coefficient or Pearson correlation coefficient, or the non-parametric equivalent, which is Spearman correlation coefficient. The other type of correlation was partial correlation. And the third type was regression analysis, for which we have two types, single and multiple regression analysis. And finally, we talked about chi-square test. And we said that this is the most important non-parametric test which everybody use in second language research. This is the end of session 11. Good luck, everybody.